video, we're going to look at ways to find the area between a curve and the x-axis, starting by using an estimation process involving a finite set of rectangles. Looking at the first picture on the left, suppose we wanted to figure out what the area of that blue region is. The area between the curve of 1 minus x squared, the x-axis, and the y-axis. Because this isn't a figure that is something we know how to find the area of, we're going to look at this process on the right, taking a series of rectangles to use as maybe an estimate for what the area might be. Looking at picture A to start. We have two rectangles that we've drawn. We're looking at the region between x equals 0 and x equals 1, and we've split that in that interval into two equal parts. So we've got that 0.5 in the middle. And then in this case, we use what's called the upper rectangle, where we're using the height of the rectangle ending up so that we've got this pink region outside the curve. So we know that this is going to end up being an estimate. So the height of the rectangle of the first rectangle, let's call it r, little r1, and let's call this one little r sub 2. We're going to say that our estimate for the area, region capital R, is little r1 plus little r2. We're looking at each of those rectangles, base times height. The base of that smaller rectangle is 0.5. And the height of that rectangle is, it looks like it's going to be 1. And then the base of little r sub 2 is also 0.5. The height of that rectangle, though, is here, which is taking 0.5 and plugging it into the original function. If I plug 0.5 in, I get the output value of 3/4. So we're taking 0.5 and multiplying it by 0.75. So our estimate here, multiplying this all together, is going to be 0.875 for the area under the curve. We know that this is an overestimate because, as we can see, these rectangles are going outside of that region, capital R, that we're trying to find. Looking at picture B, what we're doing now is taking smaller subdivisions of the interval between 0 and 1. Rather than having the base of each rectangle be 0.5, we're taking the base to be 0.25. And this is going to give us a slightly more accurate estimate because the area of error, that pink part that's outside the curve, is going to be smaller. But we're using a similar process where, in this case, we'll have 4 rectangles. And let's say that R1 is going to be, the base is 0.25. And the height, again, is here, 1. The second rectangle base is 0.25. The height in that case is 15/16. I'm getting the height by taking this point here, 0.25, plugging it into the original function, and the output value was 15/16. R3 is 0.25 times 3/4. And then R sub 4 is 0.25 times 7/16. Again, the process that I'm using for each of these to find any particular rectangle is taking the width of the base. In each case, it's 0.25 here because I've split the interval into 4 equal parts. And then the height of the rectangle is coming from, in this case, 0.5 plugged in to the function to figure out where this point is here. Adding all of this together, I would get for my estimate, this one is 0.78125. Again, we know that this is going to be a more accurate estimate because we've got a less margin of error outside the curve. However, we still know that it is an overestimate. So what would happen instead if we looked at the lower rectangles? Looking at picture A on the left, instead of having the height of the rectangle be outside the curve, in this case, the height of the rectangle is underneath the curve, and that light blue area you see is going to be a different error where we have an underestimate. I would still use the same process to figure out the area of each of these rectangles. This last rectangle here, the height of it is 0. So this is our sub 4 technically, but I can see that the height of that is 0. But for these lower rectangles, I would still use base being 0.25. And in this case, the height, instead of being 1, the height is coming from 15/16. When I have a function like this that is decreasing, if I have a function that is decreasing, and I'm thinking about drawing rectangles, if I'm thinking about an upper estimate, then that height is going to come from from the left-hand point. But if I have a function that's decreasing and I want to take the lower estimate, then that height is going to come from the right-hand point. So depending on whether the function is increasing or decreasing will help us determine whether we're taking the left end of a particular interval or the right end of a particular interval. Picture B here is maybe thinking about splitting the difference between that error of the upper rectangles and the lower rectangles. What if instead I were to select, let's say, the midpoint and have that be the height of the rectangle? In that case, maybe I'm kind of finding the best of both worlds where I've got a little bit of overestimate and a little bit of underestimate. What I mean by that is looking at, let's say, this second rectangle, R sub 2. I have a little bit that's overestimate and a little bit that's underestimate, and maybe those would balance each other out. Similarly here, maybe this and this, maybe those are almost exactly the same. So again, we have 3 different ways that we can have this estimate using an upper triangle, an upper rectangle, a lower rectangle, and a midpoint rectangle. Obviously, the smaller that I make the widths of the rectangle, or the more rectangles that I have, the better the estimate is going to get. So this picture shows what it would look like if I had 16 upper versus lower rectangles. And this chart gives us the calculations for going up to 1,000 subintervals, looking at the lower sum, the midpoint sum, and the upper sum. And we can see in this last row that as we increase the number of rectangles that we have, decreasing the width of them, those estimates become pretty close together. Here's an example problem that we can use. The velocity function of a projectile fired into the air is given. And we're going to use the summation technique that we just talked about to see if we can estimate how far the projectile rises during the first 3 seconds. Now, this chart here has some of the data that we could figure out using this upper and lower sum idea, but I'm going to show you how we would do this mathematically to come up with these numbers. We want to know how close our estimate is to the actual value of 435.9 meters. Next week, we're going to be talking about more specific techniques that'll help us figure out what that exact value is. Well, let's think about what we learned before. We know that the position function s of t is the antiderivative of the velocity function. So if we took the antiderivative or the integral of the velocity function, we could get the position function back, but we know that there's this potential constant that's added. And in the original problem that we have here, we weren't given any conditions. We don't know anything specific about a particular position and time. And so we don't have a way to determine what c is. And so what we're going to do instead is use the velocity to estimate the distance. We know that distance is equal to velocity times time. We have a certain time interval that we're considering. We have the velocity function, so we're going to go kind of backwards to figure out what the distance is. So let's think about a timeline here. Let's have this be 0 seconds, 1 second, 2, and 3 seconds. Let's call this point t sub 0, t sub 1, t sub 2. These are particular time blocks. I'm breaking up the interval between 0 and 3 seconds into 3 definitive sections. So this right here is going to be what we call delta t, or the change in time, 1 second in this particular case. And the original function that we had, which is 160 minus 9.8t, we know that that's a decreasing function. It has a negative slope. So if I think about a function that is decreasing and I want to calculate the upper sums, let's take 2 points in time. The upper sums are going to come from the values on the left. So to get these rectangles that are called the upper sum, where we're having this overestimate, this part that's above the curve. So to calculate the upper sums, we're going to take those 3 points that are on the left at time equals 0, at time equals 1, and at time equals 2 seconds. This is 3 seconds over here. So we think that the distance through our approximation is going to be plugging t sub 0 into the function. Actually, let's call it v. And then multiplying by the change in time, 1 second. And then v sub t1, plugging 1 second into the function, multiplying by the base is 1 second. And then v sub 2, v of t sub 2 multiplied by delta t. If I plug 0 into the function, I'm going to have 160 minus 9.8 times 0. And then I'm multiplying by delta t, the change in time is 1 second. If I plug 1 into the function, 1 second, I'll have 160 minus 9.8 times 1. And then again, I'm multiplying by 1 second. And then at 2 seconds, I have this for the velocity, and I plug 1 second in. Each of these brackets are the height of the rectangles, and then each of these are the bases of the rectangles. So adding all that together, the estimate that I'm getting is 450.6 meters. Now, what I'm going to do next is repeat the process, but instead I'm going to calculate the lower sums. In this case, if I wanted to think about the lower sums, let me draw this. I'm going to use the rectangles drawn from the left-hand side so that I have this underestimate. So now, instead of using T0, T sub 1, T sub 2, I'm going to use T sub 1, T sub 2, and T sub 3 as the heights of the rectangles. Same process. My new estimate is going to be the velocity at T sub 1 times delta T, the velocity at T sub 2 times delta T, and the velocity at T sub 3. So I'm going to have 160 minus 9.8 times 1, again multiplied by 1 second. 160 minus 9.8 times 2, and 160 minus 9.8 times 3. And this estimate comes out to 421.2 meters. So we know that the actual value is going to be somewhere between 450 and 421. Looking back at the original, using more advanced techniques, we know that the actual value is 435.9. So let's estimate what the error is in this process that we're using. So the error, the magnitude of it, is going to be the true value minus the calculated value. Using an estimate, looking at the absolute value between them. We just saw that the true value using advanced integration techniques is 435.9. If I go back and look at this table that I had at the beginning, if I were to take 192 subintervals, it looks like the lower sum here is 435.67. So I'm going to take that to be my best estimate. So I'll subtract 435.67. And that gives me 0.23. And just double check that, 435.9 minus 435.67. So then if we want to talk about the error percentage, we'll take that magnitude in error, 0.23, and divide it by the actual value, 435.9, and that gives us about 0.05%, pretty small error. So the point of this is that even just taking 192 subdivisions, we're getting a pretty decent estimate for what the actual, in this case, distance traveled is. All right, thank you for watching. We will do more examples like this in class.